Hello dear students, I'm Dr. Moin. In this video we are going to discuss about thermo-mechanical analysis TMA, which is the type of thermal methods of analysis. So let's start it. So here are the contents of current video. In this video we'll see the basic introduction of thermo-mechanical analysis, then we'll see its basic principle, then we'll see the various mechanical moduli, and in the end we'll see the instrumentation of this technique, thermo-mechanical analysis. So let's start with introduction. The mechanical properties of materials provide an essential information about their suitability for particular usage. Means by knowing the mechanical properties of various materials, we may conclude that for what type of purposes these materials can be used, and can indicate how the material has been treated before testing. And it also tells us, these mechanical properties also give us information that how they are prepared, means what type of properties they do have. The molecular nature of the material will be most important in determining their mechanical properties. So mechanical properties, they depend upon the composition of that material, that what type of molecules are present in that material. For example, the behavior of plastics will be very greatly influenced by their chemical structure. Definitely, if we are talking about the plastic, so its properties, its characteristics, they will depend upon its chemical structure, which type of molecules and how they are attached with each other. Either the chains are linear or they are in cross-linking, and their blending, that is with what type of material they are mixed, and the way in which they have been fabricated, mean how they are formed, what is the composition. The mechanical methods are divided into two classes, and these depending on whether the forces applied on them are constant or varied. So these methods are divided into two classes, and these depend upon the forces applied on these materials, whether these are being applied constantly or these are being varied. And very often the parameters and the properties which are measured are specific to the method. So these depend upon mostly on the method, but can still be extremely useful in comparing materials. So by using the method, the various properties of materials can be compared with each other. So here is the principle of this technique. And what is this? This is a technique in which the deformation of the sample under non-oscillating stress is monitored. Means the stress is being applied on sample and stress is non-oscillating. And what type of deformation is going to happen in sample, that is monitored against time or temperature, while the temperature of the sample in a specified atmosphere is programmed. So temperature is properly programmed and the atmosphere is specified, mean what type of atmosphere you have given to your sample. So we study the deformation of sample under this non-oscillating stress. Now, the stress may be compression, some sort of compression, or this may be the tension to our sample. This might be the flexure, some sort of bending, or torsion, might be some sort of twisting. And if the stress is too low to cause deformation, means stress is too low, that is unable to cause deformation, then in this case TMA monitors the dimensions of the sample, and this role can be called thermodilatometry. So thermodilatometry is a technique in which we measure some sort of volume changes in the sample by the mean when temperature is applied to the sample. So in this way we can calculate the dimensions of our sample. And this was when the stress was non-oscillating, but stress was oscillating too. So if the stress is oscillating, the technique is called dynamic load thermo-mechanical analysis, dltma. Now we are going to see the mechanical moduli. Whenever a sample is subjected to a force, it may behave in a variety of ways. A large force suddenly applied, it may break the material, but a small force that may cause deformation in it. So it's quite simple. While in case of liquid, whenever a force is applied, so liquid will flow when a force is applied, and it totally depends upon the viscosity of that liquid. Means the rate of flow will depend upon the viscosity of liquid, viscosity, and here is the sign eta. Some solids may deform elastically. So whenever the force is applied upon solids, so the deformation may be elastic. And what is this? That is returning exactly to their former shape and size when the force is withdrawn. So when force is withdrawn, so they return to their previous shape and size. While other solids, they may behave viscoelastically. Means they may show both the properties of viscosity and elasticity. That is, showing behavior which incorporates both flow and elastic deformation. With many materials, there is an elastic limit, above which the material undergoes plastic deformation, which is irreversible. Means for every type of material, there is the limit for elasticity. So if we apply the force beyond that limit, so elasticity is lost, and there is the deformation which is totally irreversible. And the further increase in the load eventually causes fracture, and if we increase the force or load further, so it may cause fracture in the substance. The parameters, symbols, and terminology that will be used for studying mechanical properties must be established. So now we are going to see the various parameters, symbols, and terminologies which are being used in this thermo-mechanical analysis technique. So first of all, we are going to see the stress. The stress is the force applied per unit area. So here is the definition of stress, that is, it is the force applied per unit area, and there might be different types of stress. For example, a normal tensile stress, and it is denoted by the symbol sigma, and that is force per unit area. Another type of stress is a tangential or shearing stress, which is represented by the sign tau, that is also equal to force applied per unit area. Another type of stress, and that is the pressure change, which is represented by the sign delta P, and that is also the force applied per unit area. And all of these types, they have the same units, that is Newton per meter square or Pascal. And here are the various types of deformation which are shown over here. So A is for when the stress is tensile stress, and B is for the shearing stress. So for example, here is the material, the original material, and when we apply the tensile strength, when we apply the force over here, so this is the length, so there might be elongation, means there might be the change in length, delta L. And here in the B, you can see this may be the original diagram, this may be the original shape of this material. And when we apply the stress in this way, so there is the deformation. You can see it is converted from here to here. Okay. So this stress will cause a deformation. So definitely when we apply the stress, it may deform our material. And this deformation, it is measured by the term strain. And what is strain? Strain, it is the deformation per unit dimension. Strain is the deformation per unit dimension. For example, there are again various type of strains. So first one is the tensile strain or elongation, which we talk about here, the elongation, and it is represented by the sign epsilon, and that can be calculated by change in length per unit length, means what length is change over here, so that is delta L divided by the actual length. So delta L over L, this will give us the tensile strain or elongation. Another type is the shear strain, and it is represented by sign gamma, and it can be calculated by this delta X over Y. So we can calculate in this way the shearing strain. Another strain is the volume or bulk strain, that is represented by the sign theta, and that is definitely for the volume. If we are measuring the volume, so that is equal to change in volume per unit volume, and strain has no unit. For an elastic material, Hooke's law applies, and strain is proportional to stress. So for elastic material, strain becomes proportional to stress, the constant being the modulus. So here we can calculate the various moduli by doing stress over strain. So now we'll see the various moduli which can be calculated with the help of these stress and strain. So first one is the tensile or Young's modulus, and that is represented by this sign capital E, and this can be done by doing the tensile stress over tensile strain, sigma over E, epsilon. So by doing this, we can calculate the tensile modulus or Young's modulus. Then we can calculate the shear modulus, which is represented by the sign capital G, and this can be done by doing the shearing stress over shearing strain, that is tau over gamma. So this will give us the shear modulus. And the third modulus is bulk or compression modulus, which is represented by the sign capital K, and this can be done by the pressure stress, that is delta P, dividing by the bulk strain theta. So this will give us the bulk modulus. So in this way, various moduli can be calculated. Now we will see the apparatus of TMA. Some equipment uses optical or mechanical measurements, while many modern TMA systems, these are using the linear variable differential transformer, LVDT, and it is being used to produce an electrical signal. So the signal produced by this technique are the electrical in nature, which are going to be produced from any type of linear movement in the sample. Now this LVDT, this consists of two mutual inductances with a common ferromagnetic core. And what happens there, with any linear movement inside, there is the magnetization of the core by the primary coil. And this magnetization in the primary coil, it induces a current in the secondary coils. And if a pair of symmetrically placed secondary coils are connected in series oppositions, if these are used, then equal but opposite signals are produced when the core is at the center point. So this type of setting, this will produce the, the proper signal. When the core is displaced, the net signal increases. And by using a phase sensitive detector, means the detector which is phase sensitive, if there is any change in phase, so it will detect. So a good linear relationship between displacement and output is obtained. So we can obtain various moduli in this case. And here is the schematic diagram of TMA apparatus. So we can see here is the sample, and here is the sample support, means sample is put on this support, and here is the furnace. If we want to give some sort of temperature, so we have put furnace inside. So all of these things are enclosed here in this compartment. So environment, or environment can be controlled, means whatever type of gases you put inside, so you can do it. Then here is LVDT, which we have seen earlier. LVDT, primary coil, secondary coil system, all of them are here. And here is the probe. You can see here is the probe. So when we push this probe inside downward, so stress can be applied on the sample and vice versa. And this stress that is being controlled from here. So here is the force control. Here is the programmer. So means there is a program series of heating. So programmer is here, and here is the sensor amplifier which senses this stress over here, and here is the recorder, and we get the final result on the computer screen. So this is all about the schematic diagram of TMA apparatus. And here is the further explanation of the schematic diagram. The LVDT is attached to a quartz probe, means the probe is made up of quartz, and LVDT is attached to it, so shown in the figure. And this probe which rests on the sample, so shown over here, enclosed in a closed atmosphere, and sample is enclosed in a closed atmosphere, and the sample holder if necessary, so there might be sample holder, and the whole assembly is enclosed in the programmer controlled furnace. So here is the furnace, and the temperature inside is totally programmed. For work below room temperature, if we want to work below room temperature, we may require another assembly. And what is that? The assembly is cooled by placing a Devar flask of liquid nitrogen around it. So we use a Devar flask of liquid nitrogen, which is used to decrease its temperature below room temperature. Then we must have to keep another thing in our mind, and that is the force exerted on the sample by the probe. Mean this way, if we apply force by the probe on the sample, it will affect the thermo-analytical results obtained. So we must keep this point in our mind. So since force can disturb our results, so for this reason an additional unit is added which can control the force. So force can be controlled, so using mechanical or computer system. So this can be done mechanically or by using in the computer system, by using the software, through software, so that we may apply a compressive force or tension, or even a zero force for dilatometry, or an oscillatory force if we are working with the dynamic measurements. So all of these things are now possible mechanically, or even these are being done by using the computer system. And here below there are typical probes which are being used for TMA measurement. So here are different designs of the probes which are being used. So these type of design, these are being used for the compression mode. Then in tension mode, here are the designs of the probes, different designs. And for dilatometry, this is the design of the probe which is being used. And some more information about probes is being listed over here. Probes of higher area will exert less pressure on the sample. Mean higher the area of the probe, it will exert lesser pressure on the sample, because we know that pressure is equal to force applied per unit area. So greater the area, lesser will be the pressure. While those with a sharply pointed or small area or a rounded end, they will tend to penetrate the sample. So if the probe has this type of shape, and when stress will be applied, so they may penetrate the sample. So these things must be kept into the mind. Then special attachments will allow the same apparatus to be used for flexural or bending measurements. So if we are interested in these type of measurement like bending, flexural measurement, so some more attachment are done with the apparatus to do these activities. The probes may be loaded manually manually they may be loaded, or this may be done by electromagnetically, and that is done by using the force control system. So dear students, this is all about the part 1 of thermomechanical analysis. So thanks for watching. If you like my video, like it, and if you didn't subscribe my channel yet, then subscribe it right now to get in touch with the part 2 of TMA. So thanks for watching. Thank you very much.